Good morning, ladies and gentlemen, boys and girls, friends and neighbors. So, a lot of today is going to be, well, the first part is going to be a little bit of a review, and then we're going to end up with a very important topic of continuity at a point. What does it mean for a function to be continuous at a point? Before we go there, we need to have a little review of what in the world a limit is. Well, a limit asks what a function value, a y value, gets close to as x approaches some x value. And note here that the limit as x goes to a of y, that's the same as the limit as x goes to a of f of x. These are both the same statement, so there's no difference here between those statements. And I'm going to start off with a graphical explanation, and then we're going to end up with an analytical that's going to be similar to what I'm going to ask you to do this week as an assignment. Okay, so here I have this graphical example. I have the blue is the graph of some function. Okay, I ask you to do some limits here. The limit as x goes to -2 of f of x. Well, I can see and keep in mind a limit asks what a function value gets close to, not what the function value is. So if I'm looking at -2 right here, and I'm going to -2 from this direction and from -2 this direction, x, then that function values are getting closer and closer to 1. In like manner, the limit as x goes to 1 of f of x. What does the function value get close to as x approaches 1 from the left? Let's do this in green. As x approaches 1 from the left and x approaches 1 from the right, those function values, you betcha, they go to 0. And then in like manner, this rascal right here, the limit as x goes to 4 of f of x. We want to know what that is. Well, I'm going to ask myself, as x goes to 4 from the left, as x goes to 4 from the right, where does the function value, where does the y values approach? Well, you can see that the y values are approaching 0. f of 4, take a note here, f of 4 is equal to 2, which does not equal 0. And likewise here with this guy right here, f of -2 is 2, which does not equal 1. Okay, so now if I add this dude right here, this is going to present some problems here. The limit as x goes to 2 of f of x. This is going to present some problems because as I approach 2 from the left, as I approach 2 from the right, the function values go to two different places. That's interesting. It's not that interesting. It's pretty straightforward. This limit does not exist. And before I can formally tell you why it doesn't exist, and we had some talks about this on a previous video, it doesn't exist because I need to talk about the left-hand and right-hand limits. And so if I go, I think I did this, f of -2 is 2 before I change page. This was 1 and f of 4 was 2 as well. Okay. So what I need to do is figure out why this doesn't exist, or come up with some idea of why that doesn't exist. And then in order for me to do that, I have to talk about one-sided limits. Okay, this means this here as x approaches a from the left. That means I'm approaching a from the left. This means I'm approaching a from the right. Okay. If as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, if this is true, then I can say this, the limit as x goes to a of f of x exists. Well, let's be more formal about that. Equals L, where L is a real number. And this is the definition of a limit. L is a real number. But what has to happen for that limit to exist? The left-hand limit has to equal the right-hand limit. As x approaches a from the left of f of x has to equal as x approaches a from the right of f of x. This is the definition of a limit, okay? And I can see here, I'll do some examples here, as x approaches -2 from the left. As I approach -2 from the left here, where do my function values go? Well, my function values then are going to go to 1, okay? As I approach -2 from the right, this dude right here, where does f of x approach? F of x goes to -1. Therefore, this limit here, since the left-hand limit does not equal the right-hand limit, 1 does not equal -1, this limit we say does not exist. And that's why that limit on the previous page did not exist. So that does not exist. I think we're going to do this guy here. Oh, sorry, that didn't go with that. I apologize. So what do these two statements tell me? They tell me this, that the limit as x goes to, let me differentiate that somehow. This tells me that the limit as x goes to -2. Let me see where I can write it. This, the limit as x goes to -2 of f of x does not exist. Okay, because the left hand doesn't equal the right hand there. And so now here, if I look at a completely separate example here, I look at these two limits, and now I'm approaching 2 from the left, which is this guy, and then I'm going to approach 2 from the right, and I'm going to see if those two limits exist. Well, as x approaches 2 from the left, where does the function go? It looks like the function is going to go to 1. As I approach 2 from the right, where does the function go? The function approaches 2. So what can I say? You betcha. I can say that this limit as x goes to 2 of f of x does not exist. Since the left-hand limit doesn't equal the right-hand limit. Okay? I did the same thing over here. Check this out. The limit as x goes to 4 from the right is 1. The limit as x goes to 4 from the left, as I approach 4 from the left and 4 from the right, they both equal 1. And hey, this limit does indeed equal 1. Since the left hand, the right hand does indeed equal the right hand. This is going to lead us to the very important topic of continuity. So we're going to talk about continuity at a particular point. Okay? And I'm still going to do a graphical example here. So let's move this rascal out of the way here. A function is continuous at x equals a if and only if the limit as x goes to a from the left of f of x is equal to, here's the difference between when a limit exists and when a function is continuous. Here's the one piece of this equation. So the left-hand limit has to indeed equal the right-hand limit, but they both have to equal not only L, they have to equal, and now my L is going to be this guy here that we're going to call f of a. If this statement is true, then a function is continuous at x equals a. This is the definition of continuity, ladies and gentlemen. This is the definition of continuity. Okay? So let's see here. Let's do an example here. Why is this function discontinuous? It's obviously, we could do the pre-calculus definition. This function is discontinuous at -2 because when I'm sketching the graph, I have to pick my pencil up. And this thing is continuous at 1. I just put that point there because I don't have to pick my pencil up. So why is this thing, analytically, why is this thing discontinuous at -2? How would I write that? Here's how I would write that. I'm going to have to use this statement here. I'm going to have to use this definition of continuity. I have to use that. So what I'm going to do is I'm going to look at the limit as x goes to -2 from the left. Okay, and I'm looking at -2 from the left. And I'm going to look at as x goes to -2 from the right. And I'm going to evaluate f of -2, and I'm going to see if this equation holds true. If this is equal to that and is equal to that. Well, let's do this limit right here. The limit as x goes to -2 from the left of f of x. Oh, that y value is approaching 2 right there. So this dude right here is 2. What is f of -2? What is it? It's that solid circle. It's 2. As I approach -2 from the right, what does the y values approach? Well, that's kind of scary. Something fell in there. What do the y values approach? They approach 1. So this statement right here tells me that this function is discontinuous at -2. This is the analytical reason why f of x is discontinuous at x equals -2. I don't know what these guys are here for. Okay. Now we're going to jump down here and we're going to do an analytical problem. This was a graphical problem. It's kind of easy to see. I mean, I could just look at that graph and say, oh, this thing is discontinuous at -2. But if someone asked me, hey, give me an analytical reason, this would be the analytical reason that this statement and this statement would be the analytical reason that f is discontinuous at -2. So let's jump down here and let's look at an analytical. Let's look at a piecewise function here. Let me get this guy right here. Put him over here out of the way so I can see something. Okay, so I have this piecewise function. It's 2 pieces. I have the piece 1 minus 2 sine of x if x is less than or equal to 0 at the top piece. And I have the bottom piece e to the -4x if x is greater than 0. And I could look at the graphical representation of this particular piecewise. I could graph that, but we don't have to. What we're going to do is show that f of x, we're going to show f of x is continuous. Here's our problem. We're going to show that f of x, which is this piecewise function, is continuous for all real numbers. In the first statement I'm going to make, if I look at 1 minus 2 sine of x, that's continuous for all real numbers. This particular piece, that's continuous for all real numbers. So if this is continuous for all real numbers, as it is, 1 minus 2 sine x is continuous, and note when x is less than 0. The other thing that I can certainly make a statement that this guy right here, e to the -4x, same thing, is continuous for all real numbers. I mean, I know this. This is exponential, domain is all reals. This is trigonometric, domain all reals. This is continuous for all reals. If that's the case, as it is, then e to the -4x is continuous when x is greater than 0. So my only question, my only concern is what happens at x equals 0. Is this thing, so here, that's my question right here. Let me go down here. So my question is this: is f of x continuous at x equals 0? That's my question. Oh, well, guess what I'm going to do? I'm going to use the definition of continuity at a point, and here's that definition. Where did I put that at? Okay, here's the definition that I'm going to use right here. A function is continuous at x equals a if and only if the limit as x goes to a from the left is equal to f of a, which is also equal to the limit as x goes to a from the right of f of x. So I'm going to have that statement. So if I come down here, and let's write that statement out. Let's just write that statement out because I want to see. So here's what's going to happen if this function is continuous at x equals 0. The limit as x goes to 0 from the left of f of x has to equal f of 0, which has to equal the limit as x goes to 0 from the right of f of x. So what we're going to do is we're going to look at all these pieces, because I can do that. We're going to look at each, there's 3 pieces there. We're going to look at all 3 of these pieces. We're going to look at this piece, and this piece, and see if they all equal. If that equation holds, then the function is continuous at x equals 0, and then the function would be continuous for all real numbers. So let's look at this. What happens over here? If I'm approaching 0 from the left, that means what? That means that x is less than 0. So I'm just going to come up here, and then I'm going to do direct substitution, because I want to get ever so close to 0. I'm going to get ever so close to 0. Okay? As x approaches 0, ever so close to 0 from the left, and all I'm going to do is do a direct substitution. I'm going to put 0 into this guy right here. Okay? Which is going to be 1 minus 2 sine of 0. Okay? Hey, what is that? Well, the sine of 0 is 0. 2 times 0 is 0. So that's going to be 1. And now I'm going to look at f of 0. Well, when is x equal 0? X is equal to 0 up here at this top piece. So well, that was convenient, because that's going to absolutely equal the left-hand limit. So that tells me right here that that is also equal to 1 minus, put that in blue here, 1 minus 2 sine of 0, which is equal to 1. Okay? So now we're going to look at this piece right here. Okay? So now, what do I know about this piece? This piece here, I know that if I'm approaching 0 from the left, I know that x is going to be greater than 0. So what piece am I going to look at? I'm going to look at this piece right here. And I'm going to get ever so close to 0 from the right there. X is greater than 0. If I just did a number line right here, bam. And I'm going to go to 0. What am I doing? I'm approaching 0 from the right here. Okay, because when I'm greater than 0, it's e to the negative 4x. So I'm going to just put 0 into that, do some direct substitution, and that's simply going to be e to the negative 4 times 0. And what's negative 4 times 0 is 0. What's e to the 0 is 1. So hey, that statement is indeed true. So now I have got to have this statement. This is the statement that's most important. Well, both of these statements together are important. This statement, and then when I evaluate each of the limit, that's important. Now I can make the statement, hey, f of x is indeed continuous at x equals 0. And since it was continuous everywhere else, f of x is continuous for all real numbers. So you will have a free response question on an upcoming assignment that has you do a problem similar to this problem right here, where you have to show that the function is continuous for all real numbers and have some discussion. Keep in mind you need these 2 parts as well. You need this and you need this, and then you're going to need the limit definition for continuity at a point. Okay, so we're at about 20 minutes. I want to limit my videos to 20 minutes. Keep in mind you can always pause the video, rewrite it. Don't make this more difficult than it is. The most important thing about this is the analytical work that you're going to have to show to get your points. All right? All right. See you.